All right, so I think it's now that I have a captive audience here, I think it's good to understand random probabilistic algorithms. All right, this picture here is a famous picture called a random walk. If he's drunk and he keeps taking steps and he goes a random, how far does he travel? And if you don't know, this is the normal distribution. What does it mean? Is, well, down here at the bottom are values. You have a random event, and you get one of the answers at the bottom, and the probability is kind of the height, right? So the most likely value you get is mu. Mu is usually used for the mean value. What is the expected value, right? You expect to get, in fact, you expect to get something in the pink region, right? It's mu plus or minus the standard deviation. Here's, what is that letter? Psi, mu minus, I forget what that letter is. Anyway,
Sigma.
Sigma. Yeah, so you expect to get mu plus or minus sigma. But the more standard deviations away you are, the less and less likely it grows exponentially small that you get that probability, right? So in a normal distribution, the value you get is likely to be mu plus or minus a few standard deviations, right? And you can see every color changes as a standard deviation. All right, so let me tell you a game which I think is kind of fun. So there are doors. There say lots of doors. I don't know if I even say how many doors there are. And behind each door, there's either a prize or there's a goat, right? And I'm promising you that half the doors have prizes, right? And what is your goal? Your goal is to come up with an algorithm, and the algorithm says, okay, open door 78, now open door 31, now open door, right? That's what an algorithm door it does, is it tells you which doors to open, right? The orders to open them. And what is the input to the problem, right? The input specifies which half of the doors have prizes, right? And so the way we normally do computation is worst case, right? The normal way is I give an algorithm and then we look at the worst case input. So what do you think the worst case running time of this algorithm is? How many doors do you have to open? Anybody have an idea?
10.
All of it?
Well, half of them have prizes, right?
Half.
So you have to look at half of them.
Half and then, right?
So n over 2.
Yeah.
And over 2, right? Yeah.
The worst case, right? So here's the game, right? So everybody we've seen this kind of line before, right? The game is, we're claiming there exists an algorithm, all right? So that we start by the prover comes up with the algorithm. It says the order in which we look at the doors. And then the adversary knows the algorithm, right? It's really an evil adversary. He knows which doors you're going to look at first, and he puts goats behind them all, right? So that means the running time is half the doors. Everybody understood that. And that doesn't seem fair, right? Because what do you want to do instead? Well, you want to look at a random door, right? So instead, we're going to think about, so quicksort, you might not have even learned, have you learned quicksort yet? Maybe not. It's a sorting algorithm that uses randomness. So this is just talking about that sorting algorithm. Let's not worry about it. It's an algorithm which in the worst case is n squared, but with high probability, it takes n log n time. All right, so now let's talk about what the game is for random in the random world, right? Again, we have to specify an algorithm, but it's going to be a probabilistic algorithm, right? So I tell you the algorithm, and what's an algorithm is it flips coins, and based on the coins, it decides what it's going to do next, right? It decides what door to open. Then it flips the coins, and it decides the door. In fact, I can tell you what our algorithm is going to be concrete here, is open a random door, and then open another random door, and then open another random door, right? So that's our probabilistic algorithm, right? And now the advantage of this is it makes all, as far as the adversary is concerned, right? The adversary knows that I'm going to open a random door, but he doesn't know the coin flips, right? So if you look ahead in the game, he has to come up with the input without knowing the coin flips, right? But so now that's what I'm saying here. He knows that we're going to open up a random door, but he doesn't know which door because he doesn't know the coin flips. So all the doors now are equivalent, right? Which door should he put the prizes and the goats behind? Well, it doesn't even matter because the algorithm is going to open up a random door, right? So it's no longer, is there a worst case place to put the doors, right? All right, and then after hey, somebody's kind of a little loud there. Could you stop being so loud? Somebody? Yeah, thanks. All right, then after the players chooses where the prizes will be, then we flip the coins and decide which doors to open, right? And so the point is that there aren't worst case inputs anymore. There's not a worst case where to put the prize. There are worst case coin flips, right? There are bad coin flips, which means that you'll never find a prize. But they happen with small probability. All right. So then after we get the coin flips, then we ask, did we find a goat or did we find a prize or not? Right. So let's analyze how the probability works. Half the doors have prizes, right? So if you look at a random door, the probability of finding a prize is what? It's a half, right? Half the doors have prizes. You look behind a random door, the probability of finding a prize is a half. So now suppose I open up T doors. Let's say our running time is going to be T. I'm going to keep opening up doors until either I find a prize or I only need one prize, right? So after I'm going to open T doors. So what's the probability I find no prizes? Well, I open up a door. It's a probability a half, no door, no prize. And then the next door, a half, no prize. The next, right? It's what's the probability I get tails T times in a row, right? It's 2 to the negative T, which is gets to be very, very small, right? Here's how I like to analyze 2 to the numbers, right? 2 to the 10, 2, 4, 8, 16. 2 to the 10 is 1,024, right? So 2 to the negative 20 is about 1 in a million.
Sorry,
2 to the negative 30 is 1 in a billion. All right.
Sorry, quick question.
Yeah.
Since you have that formula, the 2 to the minus t,
Yeah.
does that mean that the probability of opening all doors with prizes is the same as opening no doors with prizes for the same amount of coin flips?
Yeah. Yeah.
Okay.
Exactly.
So it works both ways.
Yeah. So remember the normal distribution is if you open up T, you're very likely to get T, half of the T will have prizes. And you may get plus or the standard deviation is square root of T. So you're likely to get T plus or minus some number of square roots of T's. All right. So what's the probability you find at least one prize is 1 minus that, right? So that's really, really good. So here we say that for no matter what I gave you an algorithm so that no matter what the input is, the probability of finding a prize is exponentially big, right? Is 1 minus an infinitesimal, right? Right. So here's another way of looking at the algorithm: is instead of stopping at time t, let's keep opening doors until you find a prize, right? So then the algorithm is guaranteed to find a prize, right? Here we say for every coin, no matter what your coin flips are, you're going to find a prize. Why? Because your algorithm is keep opening doors until you find a prize, right? It might take you in over 2 door openings, right? But what's the expected running time? Well, it turns the expected running time, right? What's the expected? If you flip a coin, you have a probability of a half of getting ahead. What's the expected number of coin flips until you get a tail? How many times do you expect to flip a coin? You expect to flip it 1,000,000 times before you get ahead?
Just once.
Two.
Just once, because you get it on the first time.
Well, only 50-50 you get it on the first time.
Yeah.
Right? So somebody gave the answer, the expected number is 2. Right? It's the same, say I roll a dice. How many times do I have to roll what's the expected number? If I keep rolling it until I get a 6, how many times do I expect to have to roll it?
6.
I expect to have to roll it
6 times?
Yeah, exactly. Right? So here the expected running time is 2. Does that make sense?
Yeah.
All right. Any questions
sure.
about probabilistic algorithms?
Sir,
Yeah.
quick question. Can you define all again? Because I want to make sure I know.
Define what again?
All, random in this, define all.
I don't know that word, but I can define random for you.
Yeah, define random. What does random stand for?
Random says the R. Sorry. Of course. Sorry about that.
Like in this formula or whatever.
What R is you flip coins. And so the standard way of thinking about R is it's a sequence of 0 ones that bits, right? That were chosen randomly. So you flip a coin and you get a heads or tails. You flip a coin, you get head or tail. You flip a coin, you get a head or tails. And so R is going to be as many coin flips as you need.
Can you also tell how it relates to algorithm and the other stuff?
Yeah, that's what yeah, exactly. So here I'm giving you an algorithm, and what the algorithm, here, in fact, I have it here. See here, the A sub Ri. So what that is meaning is I have my algorithm and you give it coin. So A says what you're going to do given the coin flips and given the input, right? So A says, A kind of has 2 inputs. The one input is the input to the problem, and the other input are what are the coin flips. And then A is a deterministic algorithm, just like you always write, that given its input, it's fixed what it does. But what it does depends on both the input and the coin flips. So we fix what A does as a function of R and I. And then we come up, then the adversary says what the input is. And then we randomly flip the coins. So we get random coin flips. Right? Does that make sense? And the point is that the adversary who chooses the input, he knows your algorithm, so he knows what you will do for every input and every coin flips, but he doesn't know the coin flips.
Hi, Professor.
Yeah.
What is the output of this ARI?
Oh, the output of this program is did I find a prize or not?
Oh, okay, okay.
Right. So the problem P is I don't care what the input is. What we want to do is we want to find a prize. So here I'm really saying, when I say what's the expected time, it's the expected time until you find a prize. And back here, we're saying, what's the probability that I find a prize? Well, it's 1 minus the probability I don't find a prize, which is exponentially small.
Oh, okay, that makes sense. Thank you.
Right? Good question. I just wrote it down this way that's for a generic problem. But for our problem is, do you find a prize?
Sorry, about the probability of not finding a prize, but if you flip it enough times, wouldn't you 100% find a prize if you flip it in over 2 times?
Yeah. So this one over here, in the first one, we only open T doors, right? So the time is definitely at most T, but there's some probability after T doors, maybe T is only 10, right? Maybe we have lots and lots and lots of doors, but we only open up 10 of them. So then the probability that we find a prize is 1 minus 1,000th, right? But in this time, we keep opening doors until we find a prize. So for every coin flips, we are going to find a prize, right? Even if it means we open up half the doors, we will find a prize, right? But our expected running time is 2. Right? Does that make sense? It might be that our running time is n over 2. I mean, T over 2. Not T. It might be n over 2, right? We have to look at half the doors. The running time could be we find a prize the first time. Or it could be that we don't find a prize until we've looked at half the doors. But the expected number of doors we open is 2.
Hey, Jeff, I have a question. So go back. So let's say it wasn't a coin. Let's say it was a dice.
Right.
How would it change? Would it still be 1 minus 2? It wouldn't be 1 minus 2 to the power of negative T, would it?
No. The 2 doesn't have to do with dice. The 2 has to do with the fact that I promised there was prizes between half the doors. Right? I didn't actually tell you that R was coin flips. R is just any source of randomness. So what randomness in this game, what randomness we really want is you have a dice that has n sides, right? And so we want to randomly choose a number between 1 and n because that helps us choose a random door. Right? So we tend to not think about, right? Where you get your randomness doesn't matter because you can play with it to use it however you want.
So the
right?
formula is the same. 1 minus
Yeah,
2.
so here, but what we could change is let's change the game so that I promise you that there's a prize between in a 7th of the doors, right? If a 7th of the doors have a prize, then every time I choose a door, the probability I have a prize is 1 over, the probability I find a prize is 1 over 7. So the probability I don't find a prize is 6 over 7, right? So then we multiply 6 over 7 times 6 over 7 times 6 over 7. So we would get 6 over 7 raised to the power of t.
Okay, I got it now. Yeah, so when it's 1/7, when it's 1. Yeah, so yeah, I got
Right?
it now.
That's where the 2 comes from.
Can you
it's not from the coin flips.
Can you re-explain about the 6/7 thing again? Sorry.
Yeah.
Because it's 1 minus the 1 over.
Yeah. Let's say that I put one prize, and every 7 doors has a prize, right? So the probability of find a prize is 1 over 7, right?
Right.
what's the probability I don't find no prize? It's
6
going
over
to be
7.
6 over 7 raised to the power of t, right?
Right.
I don't find a prize, 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 right?
Okay.
And just the, I mean, it's good to know this kind of math. This is approximately, well, this is 1 minus a seventh, right, to the t. And that is approximately 2 to the negative t over 7, right? And the reason t over 7 is because, well, I have to look at kind of 7 doors before I expect to find a prize, right? If 1 in 7 has a prize, then after I look at 7 of them, then I'm expected to get a prize. So actually, let's change this from a 2 to an e. You know, e is 2.17. So the probability I don't, if I looked at 7 doors, the probability I don't find a prize is about 1 in e. So then if I do that t over 7, right? T over 7 times, I look at 7 doors, then that becomes the probability. This is more math than we're going to cover right now, but everybody good with that?
Sorry, Jeff, could you explain the middle part again? I didn't quite understand.
This part?
So, yeah.
Well, I'm just saying 6 over 7 is 1 minus the 7th.
Oh, okay, wait, sorry. I misread that. I thought it was like 1 minus 1 over 7.
Oh yeah, no. I'm type right. This is
Okay. Yeah. No.
Jeff?
Yeah.
For the second slide, the next one,
Uh-huh.
where you have expected time.
Yeah.
How is the AI, PI, and the expected time are related? Like by which logical and implication? Like how are they connected?
Calculate expected time?
No, I'm saying how the first statement, where you have AI, PI,
right,
and the second statement, how are they connected?
Well, the first one says the
I know what they're saying. I just want to know like the logical connection. Like, is it by and or implication?
I see. I would say for every a there exists an a for every I, and then I have big brackets, and then I would put an and between this line and this line. Right?
Oh, okay.
Put a brackets on either side here and put an and in the middle. Right?
Okay.
Right? For every input, 2 things are true. One thing that's true is you're guaranteed to find a prize. The second thing that's true is that the expected running time is 2.
Okay, that makes sense.
Jeff, I was just wondering, so since the algorithm is random, so is it possible that every time we keep on opening the same door?
Oh, you're very good. So I was ignoring that. So it's called, this is called you choosing randomly with replacement or without replacement, right? So I completely ignored that statement. So clearly a better algorithm would be choose a random door that you keep going as you keep getting goats. And so what do you do next? You look in a random door that you haven't seen. That would make the algorithm better, right?
Yes.
But the analysis I have doesn't really care which you do. So I kept saying in this one, after n over 2 doors, you're guaranteed to find a prize. But that's only if you do it with, you don't look in the same door twice, right? if you keep choosing random new, you keep choosing doors randomly, then it's possible that you have to look at an infinite number of doors, right?
Yes.
But the probability of that is so small that it doesn't change the fact that the expected running time is 2. So I didn't mention it because, but you're right. Those when you do really precise calculations, you have to know, am I doing it with replacement or without replacement?
All right. Thank you.
Any other questions about randomness? Should we go on?